In this unit, we will be examining ways of analyzing continuous data. This covers Chapter 5 of your course textbook. To begin, let's first talk about some of the commonly used descriptive statistics for continuous data. The first is measures of central tendency. These measures help describe the typical number found in a list of numbers. Mean is one measure of central tendency. The mean is the same as the average. It is computed by dividing the sum of all values by the total number of values. The mean is also the most common measure of central tendency. However, in situations where a list of continuous variables are not normally distributed, mean may not be the best estimate of the typical value. In these situations, the median is a better measure of central tendency. The median is the middle or center number in a list of numbers. To determine the median, you must order your list of numbers from smallest to greatest and count the number of values. Then split that value in half. Whatever that number may be, count either from the lowest or highest to find the center value. The last measure of central tendency is mode. This is the value that occurs most frequently in a list of numbers. It is rarely used and is a poor way of describing the typical value in a list of numbers. Another way of describing continuous data is with measures of variance. These measures are a bit more complicated to calculate by hand, so I recommend using software for assistance. Variance is the first measure and is the average of the squared standard deviations from the mean. Thus, standard deviation is the square root of the variance. Finally, the standard error of the mean is the standard deviation divided by the square root of your sample size. All of these measures tell you how spread out the data are. That is, how far are the values from the mean. For inferential statistics of continuous data, we will be looking at the one-sample t-test, two-sample t-test, pair t-test, and ANOVAs. These are very similar to the z-tests described previously. We will begin by covering t-tests. There are three types of t-tests we're going to discuss. The first is a one-sample t-test, and the purpose is to compare the mean of one group to a standard or goal. This is very similar to the one-sample z-test, but the main difference is that we are dealing with mean values rather than proportions. The second type of t-test we will be discussing is the two-sample t-test, also known as the student's t-test. The purpose of a two-sample t-test is to compare means of two distinct groups. Again, this is very similar to the two-sample z-test, but instead of comparing proportions, we are comparing means. The other type is a paired t-test. A paired t-test compares the mean difference in two conditions from one group. Anytime you do a study where you compare before and after responses in the same group of people, a paired t-test would be appropriate. For instance, if you were to compare weight loss in subjects before and after an educational program, a paired t-test would be appropriate. You could also look at cholesterol levels in subjects before and after cholesterol-lowering medication. The main difference in a paired t-test is compared to a two-sample t-test, is you're comparing one group in two different conditions rather than two groups in two different conditions. Let's start by taking a closer look at the one-sample t-test. We use a one-sample t-test when we want to compare the mean value to a standard or goal value. The two-tailed null hypothesis is that the observed value is equal to the standard value, while the alternative hypothesis is that the observed value is not equal to the standard value. A one-tailed test would provide directionality to the differences, but is common to stick with a two-tailed test. Next, we calculate the t-stat using the equation shown on the slide. One thing I want to point out with the t-stat is that the denominator of the equation, standard deviation divided by the square root of our sample size, is actually the way of calculating standard error. We will use software to calculate the t-stat as well as the standard error. The results of the test provides us with a p-value, and if the value is less than our alpha, we can make the conclusion that we have enough evidence to reject the null hypothesis, and that there are significant differences between our observed value and the standard value. In this example, let's assume we're asking the question, is the average length of stay for patients treated with congestive heart failure with major complications and comorbidities at a specific hospital shorter or longer than the national average of 6.2 days? It is discovered that the average length of stay for the observed patients was 4.9 days, with a standard deviation of 3 days. Our null hypothesis is that patients treated with a congestive heart failure with major complications and comorbidities had a length of stay equal to the national average of 6.2 days. Our alternative hypothesis is that patients treated with congestive heart failure with major complications and comorbidities had a length of stay not equal to the national average of 6.2 days. After calculating a t-stat, we find the p-value to be less than our alpha of 0.05. Therefore, we can reject the null hypothesis and conclude that the length of stay for patients treated with congestive heart failure with major complications and comorbidities had a length of stay significantly less than the national average. We may want to calculate a confidence interval for the population mean to determine if the population is performing different than a standard or benchmark. The first thing we must do is to determine the critical value at level alpha divided by 2. This is largely dependent on the degrees of freedom. Degrees of freedom are determined by taking our sample size minus 1. So if we evaluated 20 subjects, our degrees of freedom would be 20 minus 1, which equals 19. Using a normal distribution table, we could determine the critical value with the specific degrees of freedom. We take the critical value divided by 2 and multiply that number by the standard error. Remember, standard error is determined by taking the standard deviation, s, divided by the square root of our sample size, n. The number we come up with is then added and subtracted from our sample mean to get the upper and lower tails of our confidence interval respectively. Ultimately, we could determine from the confidence interval how extreme our observed value must be to determine different from the set standard. Remember that when you want to use a one-sample t-test, you must compare the mean of one group to that of a standard value. So let's take a look at the description and requirements in conducting a two-sample t-test. Again, a two-sample t-test compares responses in two distinct groups. The responses in each group are then independent of those in the other group. Another example would be if some subjects take a treatment and another group of subjects take a placebo, and you measure some sort of response. The procedural characteristics of a two-sample t-test involves comparing two population means by looking at their differences. As such, you are comparing the mean from population 1 minus the mean from population 2 and determining if this difference is significant. The sample means and standard deviation is used for calculating the t-statistic, which can be used for determining the p-value based on Welch's degrees of freedom. You don't have to memorize how to calculate the t-statistic, but you should know what it is. Back in the day, when you had to calculate a t-stat, you had to go to a lookup table and find the p-values based on the Welch's degrees of freedom. Welch's degrees of freedom is rather complex to calculate, and we won't be covering this. However, degrees of freedom by definition is n minus 1, where n is the sample size of your group. Because if you have two distinct groups, which may differ in size, Welch's degrees of freedom is used in a two-sample t-test. Remember, when you conduct a statistical test, the test is assessing the accuracy of the null hypothesis. You either accept or you reject the null. Thus, it is always a good idea to consider what the null hypothesis is prior to conducting a statistical procedure, and consider the alternative hypothesis as well. In the case of the two-sample t-test, the null hypothesis would be the mean from population 1 is equal to the mean of population 2. Consider this for a moment. If you want to compare running times of men and women in the 100-meter dash, the null hypothesis would be that the mean for men is equal to the mean for women. The two-tailed alternative hypothesis would be that the mean for men is not equal to the mean for women. Thus, the two-tailed alternative hypothesis would be the mean running time for men is not equal to the mean running time for women. If we wanted to add directionality to the alternative hypothesis, we could, yet this might cause problems if we predict incorrectly. This would be considered a one-tailed hypothesis. For instance, we could set the alternative hypothesis as mean time for men is less than the mean time for women. However, if mean time for women is actually less than mean time for men, then we would miss this. Therefore, a general rule of thumb is to stick to a two-tailed test unless you are certain of directionality. After you define the hypotheses, the next thing to do is to calculate the t-stat, then determine the p-value, followed by making conclusions. The conclusion would be whether you accept or reject the null hypothesis. Let's assume there is a difference in the mean times for males and females in the 100-meter dash. The conclusion can be stated as such. There is enough evidence to reject the null hypothesis, which suggests that the mean 100-meter dash times for men and women are significantly different. There are two assumptions that must be met when you conduct a two-sample t-test. The first assumption is that the groups are comparing are independent random samples. This simply means that each group is distinct, but are randomly selected in order to minimize bias. For instance, if you were to compare male and female running times, I would randomly select males to be in one group and randomly select females to be in another group. I would not bias the selection by only using athletes in the male sample while not applying the same criteria to the female sample. The second assumption is that the groups are normally distributed. That is, we aren't only comparing the super fast and super slow people. We want to assess differences in groups that when you look at the histogram of each group, it looks like a bell-shaped curve. The reason for this assumption is that we are comparing means, and a mean is representative of a sample when it does not fit a normal distribution. The median is actually a better representation of data that isn't normally distributed. For our second example, we wanted to compare average systolic blood pressure in hypertensive subjects that either take a medication or take a placebo. Our null hypothesis for a two-tailed two-sample t-test would be that subjects taking the placebo have equal systolic blood pressure to subjects taking medication. Our alternative hypothesis is that the subjects taking the placebo do not have equal systolic blood pressure to subjects taking medication. As you can see, the placebo group has high systolic blood pressure than the medication group. We could use a two-sample t-test to compare the mean systolic blood pressure plus or minus the standard error of the mean between these two. If we were to compare the means plus or minus the standard error of the means, we see that there is very little crossover between our error bars. Therefore, it's likely that the two-sample t-test would show a p-value less than our alpha of 0.05, thereby establishing that we can reject the null hypothesis and conclude that the placebo group has significantly higher systolic blood pressure than the medication group. Remember that when using a two-sample t-test, you're comparing different subjects in two different groups. Let's now shift to examining a pair t-test, which is very similar to the two-sample t-test and often confused with one another. When using a pair t-test, we compare responses of the same group in two different situations. For example, we could compare some response in subjects taking a treatment and then the same subjects taking a placebo. A pair t-test actually assesses the difference in population means under two distinct conditions. Again, a t-stat is calculated in order to determine the p-value based on the degrees of freedom. The t-stat for the pair t-test is calculated differently than the t-stat for the two-sample t-test. Also, note that the p-value is determined using degrees of freedom n-1 rather than Welch's degrees of freedom. This is because the sample size is the same in both conditions. The difference between a paired t-test and a two-sample t-test can be confusing for many. Therefore, I want to provide you an example for clarification. Let's say there are two conditions, a placebo condition and a treatment condition. The same subjects are in both conditions, where the order they receive each is randomly selected. Therefore, half the people will be randomly selected to take placebo first, then the treatment, while the other half of subjects takes the treatment first, then the placebo. After each condition, the subject's serotonin levels are measured. In a paired t-test, you compare the difference in responses between these two conditions. Therefore, for each subject, you calculate the difference. So for subject 1, their serotonin level after taking placebo was 12.6, and after taking the treatment was 13.8. Since 13.8 minus 12.6 is equal to 1.2, that is the difference. You do that for all the subjects. Then take the mean of the difference. You do not compare the mean placebo to the mean treatment. Otherwise, you'd be conducting a two-sample t-test. Rather, you compare the mean difference between placebo and treatment. If the mean difference is significantly different than 0, then you have enough evidence to reject the null hypothesis. Which brings us to the next slide. When defining the hypotheses for a paired t-test, you are assessing the mean differences. The null can be stated as such. The mean difference is equal to 0. For instance, the mean difference in serotonin for subjects taking placebo or treatment was equal to 0. The two-tailed alternative hypothesis, therefore, would be the mean difference is not equal to 0. Or you could state a one-tailed alternative hypothesis and add directionality, where the mean difference are greater than or less than 0. After stating the hypotheses, you calculate the t-stat, determine the p-value based off the degrees of freedom, and state your conclusions. The conclusion for our example may be the following. There's enough evidence to reject the null hypothesis, which suggests that there is a significant difference in serotonin levels after a subject takes placebo or treatment. The paired t-test has two assumptions. The first is that the sample is randomly selected. Obviously, each condition would have the same sample size since the same subjects are in each group. If a subject doesn't partake in one of the groups, you must drop them from your analysis. For instance, if one of the subjects only took the placebo but did not take the treatment, we cannot calculate a difference in their serotonin levels. Thereby, they should be eliminated from the analysis. The sample should also be normally distributed. Let's say we wanted to compare the mean difference in efficiency before and after EHR implementation. We could use a paired t-test and evaluate the mean difference in each doctor before and after EHR implementation. Our two-tailed null hypothesis would be that the mean difference in time before and after EHR implementation is equal to 0, while our alternative would be that the mean difference in time before and after EHR implementation is not equal to 0. Looking at the means of each group, it is likely that we would calculate a difference for each physician so that after EHR implementation, the time to complete specific tasks decreases. If we find a p-value that is less than our alpha, we could conclude that after implementing an EHR, there was a significant drop in the time it took to complete tasks. A hint for determining if a paired t-test is the correct test to use is that you often adopt the test when you're comparing the same subjects in two different conditions. Oftentimes, a paired t-test is used in studies that look at before and after conditions. Now let's move on to ANOVAs, also known as analysis of variance. There are two different types of ANOVAs we will be discussing, one-way ANOVA and two-way ANOVA. ANOVA stands for analysis of variance. The one-way ANOVA is similar to a two-sample t-test, except that in a one-way ANOVA, you're comparing means between 3 or more groups. A two-way ANOVA, on the other hand, compares two independent variables in conjunction with a response variable to assess mean effects and interactions. Like we stated already, a one-way ANOVA is like doing a bunch of t-tests. A one-way ANOVA, similar to the t-test, compares the means between groups. However, with the one-way ANOVA, you're comparing 3 or more groups. For instance, if we wanted to compare epinephrine levels after 3 distinct groups take either a low, medium, or high dose of a drug, we could use a one-way ANOVA. The test determines if at least one of the groups is significantly different than one of the other groups. A post hoc test can be done to assess each pairwise comparison and determine which groups differ. Thus, the following comparison would be made: low versus medium, low versus high, and medium versus high. There are 3 assumptions that must be met for the one-way ANOVA. Each group must be independent samples from populations that are normally distributed, and the population should have equal but unknown standard deviations. The one-way ANOVA compares 2 main measures: between group variance and within group variation. For example, the figure shows 3 groups. The blues, X's, represent the group mean, and the large green X represents the overall mean for all subjects. Between group variance compares the mean of each group to the total mean. The within group variance compares the total value for the extremes in a group to that group's mean. The MSG, between group variation, and MSE, within group variation, measures are used for calculating the F-stat in order to determine the p-value. The null hypothesis for a one-way ANOVA is the means for each group are equal. The alternative hypothesis is that not all mean groups are equal, or at least one group is different than one other group. For instance, if we are comparing the times to complete a puzzle between children ages 8 and 12, young adults ages 13 and 17, adults ages 18 to 45, older adults ages 46 to 62, and the elderly greater than 63 years old, our null hypothesis would be that the mean times to compare the puzzle, complete the puzzle is the same for each group. The alternative hypothesis would be that at least one group has a different mean time to complete the puzzle than one other group. After stating your hypotheses, you calculate an F-score based on the between and within group variance. This is used for determining the p-value, and then you can state your conclusions. A conclusion where there is a significant finding may be the following: there is enough evidence to reject the null hypothesis, which suggests that at least one group is significantly different than another group. Unfortunately, we don't know which group is significantly different. Therefore, we must conduct a post hoc test. For instance, if we compare epinephrine levels in subjects taking either a low dose, medium dose, or high dose of a drug, and find a significant difference, a post hoc test will tell us where those differences lie. The post hoc test I'm going to teach you about is the Tukey post hoc test. It basically conducts pairwise comparisons for each group, similar to conducting a bunch of t-tests. A table will then be supplied where you can see the p-values for each of these comparisons. A table will then be supplied where you can see the p-value for each of these comparisons in order to determine where the differences lie. Let's say we are a nurse manager and we wanted to compare the mean number of staff with each shift to determine if there are any differences. Let's say we collect data for each shift over a period of 30 days and we have the mean and standard error of the mean for each of the 3 shifts. We can use a one-way ANOVA to determine if there are significant differences in the number of staff between these shifts. The null hypothesis would be that all shifts have the same number of staff, while the alternative hypothesis is that at least one shift is different than at least one of the other shifts. We obtain an F-score to determine the p-value, and if our p-value is less than our alpha, we can reject the null hypothesis and conclude that at least one shift is significantly different than at least one other shift. However, we would have to use a Tukey post hoc test to look at the pairwise comparisons and determine which shift had significant differences than at least one of the other shifts. It's likely that the Tukey would find the third and first shift to be different. Therefore, we can conclude that there are significantly less staff during the third shift compared to the first shift. Remember that a one-way ANOVA is used when you want to compare means in 3 or more groups. If there are only 2 groups, you can use a t-test. Also remember that if a p-value is showing a significant difference, this means that at least one group is significantly different than at least one other group. It doesn't tell you which group is significantly different, therefore you have to use the Tukey post hoc test, which conducts a pairwise comparison and tells you which group is significantly different. Next is the two-way ANOVA, which most people have the hardest time with. A two-way ANOVA compares 2 independent variables in conjunction with a response variable. The independent variables are categorical rather than quantitative. If they are quantitative, you need to convert them into a category in some way. For instance, rather than using scales of age, you break the subjects up into age groups, such as children, adults, and elderly. An example of the two-way ANOVA would be comparing epinephrine levels by gender after taking different doses of a drug. The graph on this slide depicts this relationship, and you can see that there appears to be differences between gender, where female epinephrine increases to a greater extent than males at higher doses of the drug. The same assumptions apply to the two-way ANOVA, that is, the groups use independent samples from normally distributed populations with equal but unknown standard deviations. The two-way ANOVA measures 3 different effects. The 2 main effects assess the difference between each categorical response for the response variable. For instance, our example would measure if epinephrine differs by gender as one main effect, and the other measures if epinephrine differs for each dose. The other type is an interaction effect, where we could look at the differences between both categorical variables as it relate to the response variable. For instance, determining if epinephrine is different by dose by gender. We're going to show you 3 graphs on the right and show you 3 different scenarios. Let's look at each graph alone. You should be able to determine what the effects are. So this top graph shows 2 main effects, where there are differences between the genders. Females have higher levels than males, and differences between the doses, with no interaction effect. The middle graph shows a single main effect, where there are differences between the doses. Higher doses result in higher epinephrine levels, with no gender effect or no interaction effect. Finally, the bottom graph shows 2 main effects, where there are differences between the genders. Males have higher levels and females have higher levels than males, and differences between the doses. Higher doses result in higher epinephrine levels, and an interaction effect, where females have a greater response with higher doses than males do at higher doses. Once you see the lines deviate from each other, there's a likelihood that an interaction effect will be present. If there is an interaction effect, there should be 2 main effects as well. Thus, your goal is to oftentimes see an interaction effect, but not all is lost if you only have main effects. Because there are 3 outcomes from the two-way ANOVA, 2 main effects and an interaction effect, there are 3 possible null hypotheses. The first is that the interaction between alpha and beta are equal to 0. The second null hypothesis is that beta, one of the categorical variables, is equal to 0. And the third is that alpha, the other categorical variable, is equal to 0. The alternative hypothesis states that the interaction of alpha and beta is not equal to 0. Beta is not equal to 0, and alpha is not equal to 0. All of the null hypotheses are tested for the two-way ANOVA by calculating the f-scores and then determining the p-values. The conclusions may be as follows. There is enough evidence to reject the null hypotheses, which suggests there is an interaction effect. The groups of variable A are significantly different, and the groups of variable B are significantly different. In this example, we want to compare the mean number of colorectal screenings in men after different educational programs were provided, either online or in person. There were 3 programs, each different in terms of the content that was provided. Thus, our independent variables are program and class format, while our dependent variable is the number of colorectal screenings. We can use a two-way ANOVA to determine if the program or class format had a main effect, or if there is an interaction between program and class format. Our null hypothesis would be that the mean number of colorectal screenings are equal for all the programs. Mean number of colorectal screenings are equal for both of the class formats, and that there is not an interaction between the program and class format on the mean number of colorectal screenings. If we look at the results of our study, we'd most likely discover that the mean number of colorectal screenings does not differ between each of the programs or between class format. However, it's possible that an interaction exists if the p-value for the interaction is less than alpha. A Tukey post-hoc test might reveal that the number of colorectal screenings for men that participate in Program 1 in an in-person format were significantly different and lower than for men that were in Program 1 in the online format, and in men that took Program 2 and 3 in the in-person format. Remember that a two-way ANOVA is used when you compare one dependent variable across 2 independent variables. If you're confused on which value is your dependent variable and which is your independent variable, remember that the dependent variable is quantitative, while the independent variables are qualitative. If you ever get confused about which continuous statistical test to use, the best thing to do is to graph the data out. This will offer you hints on the best statistical test to apply. Recall that a one-sample t-test is a comparison of an average of one group to a standard value. Let's look at an example. Suppose we wanted to compare the average systolic blood pressure in hypertensive subjects to a national average. In this example, what would be your research question? An appropriate question might be, is there a difference in the observed average systolic blood pressure in hypertensive patients compared to the national average? Next, we need to state our null and alternative hypotheses. What do you think the null hypothesis is? The null hypothesis is that the average systolic blood pressure in hypertensive patients is the same as the national average. What do you think the alternative hypothesis is? The alternative hypothesis is that the average systolic blood pressure in hypertensive patients is not the same as the national average. Assume that we set our alpha at 0.05. This means we need a p-value less than our alpha to reject the null hypothesis. Remember this mnemonic. If the p is low, the null has got to go. Let's say we were to graph this out. We would show the average systolic blood pressure of our antihypertensive patients as a single bar on the plot, and the standard value, or target, as a red line on the plot. Suppose we ran a one-sample t-test with this data and we were returned with the p-value of 0.06. Is the p-value of 0.06 less than our alpha? No. Therefore, do we accept or reject our null hypothesis? We need to accept the null because our p-value is greater than the alpha of 0.05. Given these findings, what would you conclude? We can conclude that our observed average systolic blood pressure in hypertensive patients is not different than the national average. Let's look at an example of a two-sample t-test. Recall that a two-sample t-test is a comparison of an average of a variable between 2 distinct groups. Let's look at an example. Suppose we wanted to compare the average systolic blood pressure in males and females after antihypertensive treatment. In this example, what would our research question be? An appropriate question may be, is there a difference in the observed average systolic blood pressure after antihypertensive treatment when comparing males and females? Next, we need to state our null and alternative hypotheses. What do you think the null hypothesis is? The null hypothesis is the average systolic blood pressure after antihypertensive treatment is the same between males and females. What is the alternative hypothesis? The alternative hypothesis is that the average systolic blood pressure after antihypertensive treatment is not the same between males and females. Now let's assume that we set our alpha level at 0.05. Let's say we were to graph this out. We could show the average systolic blood pressure of males on a single bar, and then the average systolic blood pressure of females as another bar. Suppose we ran a two-sample t-test with this data. We were returned with a p-value of 0.002. Is the p-value of 0.002 less than our alpha? Yes. Therefore, do we accept or reject the null hypothesis? We need to reject the null because our p-value is lower than the alpha of 0.05. Given these findings, what would you conclude? Well, we can conclude that the observed average systolic blood pressure after antihypertensive treatment is different between males and females. Based on the trend observed, males appear to have a significantly higher average systolic blood pressure compared to females after antihypertensive treatment. Let's look at an example of a pair t-test. Recall that a pair t-test is a comparison of the average differences of one group in two different conditions. Let's look at an example. Suppose we wanted to compare the average systolic blood pressure before and after antihypertensive treatment. In this example, what would be our research question? An appropriate research question may be, is there a difference in the average systolic blood pressure before and after antihypertensive treatment? Next, we need to state our null and alternative hypotheses. What do you think the null hypothesis is? The null hypothesis is that the average systolic blood pressure before and after antihypertensive treatment is the same. What is the alternative hypothesis? The alternative hypothesis is that the average systolic blood pressure before and after antihypertensive treatment is not the same. Assume that we set our alpha level at 0.05. Let's see, we were to graph this out. We could show the average systolic blood pressure before treatment as one bar and after treatment as another bar. If we were to run the two-sample t-test with this data and find that we get a p-value of 0.005, is the p-value of 0.005 less than our alpha? Yes. Therefore, do we accept or reject the null hypothesis? We need to reject the null because our p-value is lower than the alpha of 0.05. Given these findings, what would you conclude? Well, we can conclude that the average systolic blood pressure before and after antihypertensive treatment is different. Based on the observed trend, average systolic blood pressure appears to be significantly lower after antihypertensive treatment. Let's look at an example of a one-way ANOVA. Recall that a one-way ANOVA is a comparison of an average of a variable between three or more distinct groups. Let's look at an example. Suppose we wanted to compare the average systolic blood pressure after a placebo low dose or high dose of antihypertensive treatment. In this example, what would be our research question? An appropriate research question may be, is there a difference in the observed average systolic blood pressure after a placebo low dose or high dose of antihypertensive treatment? Next, we need to state our null and alternative hypotheses. What do you think the null hypothesis is? The null hypothesis is that the average systolic blood pressure after placebo low dose or high dose of antihypertensive treatment is the same. What is the alternative hypothesis? The alternative is that the average systolic blood pressure is different in at least one of the groups, either placebo, low dose, or high dose of antihypertensive treatment. Assume we set our alpha level at 0.05. If we were to graph this out, we could show the average systolic blood pressure after placebo, low dose, and high dose antihypertensive treatment as our own bars on the plot. Suppose we ran a one-way ANOVA with this data and we were returned with a p-value of 0.03. Is the p-value of 0.03 less than our alpha? Yes. Therefore, do we accept or reject the null hypothesis? We need to reject the null hypothesis because our p-value is lower than the alpha of 0.05. Given these findings, what would you conclude? Well, we can conclude that the observed average systolic blood pressure is different in one of the treatment groups. But do we know which treatment group is different from one another? No. This is why we need to use a post hoc test to determine which treatment group is significantly different from each other. If we apply a Tukey HSD post hoc test, this test essentially carries out a pairwise comparisons of each group. It's like doing a bunch of two-sample t-tests. Therefore, we compare the average systolic blood pressure between the placebo and low-dose group, placebo and high-dose groups, and the low-dose and high-dose groups. We are returned with a p-value from each of these comparisons, and we might see that the p-value for each comparison is less than our alpha of 0.05. This would allow us to conclude that each treatment group is significantly different from one another, and the placebo has the highest average systolic blood pressure, while the high-dose antihypertensive treatment has the lowest. Let's look at our last example using a two-way ANOVA. Recall that a two-way ANOVA is a comparison of an average of a variable between two qualitative variables having two or more levels. Let's look at an example. Suppose we wanted to compare the average systolic blood pressure after placebo, low, or high dose of antihypertensive treatment between males and females. In this example, what would be our research question? An appropriate question may be, is there a difference in the observed average systolic blood pressure after placebo, low dose, or high dose of antihypertensive treatment and between males and females? Next, we need to state our null and alternative hypotheses. There are actually 3 null hypotheses and 3 alternative hypotheses with this test. What do you think the null hypotheses are? The null hypotheses are as follows. The average systolic blood pressure after placebo, low dose, or high dose antihypertensive treatment is the same. The average systolic blood pressure between males and females is the same. And there is no interaction between average systolic blood pressure and gender in treatment groups. What are the alternative hypotheses? The average systolic blood pressure is different in at least one of the groups, either the low dose, placebo, or high dose antihypertensive treatment group. The average systolic blood pressure between males and females is not the same, and that there is an interaction between average systolic blood pressure and gender and the treatment groups. Assume that we set our alpha at 0.05. Let's say we were to graph this out. We could show the average systolic blood pressure on the y-axis and each treatment group on the x-axis. A legend can be added to break the treatment groups down further by male and female. Suppose we ran the two-way ANOVA with this data. We would be returned with 3 p-values for each of the hypotheses. Suppose the p-value comparing the treatment groups was 0.008. The p-value comparing males and females was 0.01. And the p-values for the interaction was 0.08. Are each of these p-values less than our alpha? The comparison of average systolic blood pressure by treatment group shows a p-value suggesting we can reject the null hypothesis. The null hypothesis can be rejected for the comparison between males and females. However, the null hypothesis for the interaction cannot be rejected. Given these findings, what would you conclude? We can conclude that the observed average systolic blood pressure is different in one of the treatment groups and in one of the genders. But do we know which treatment group or across each gender is different from one another? No. This is why we need to use a post-hoc test to determine which treatment group is significantly different from each other across the genders. If we apply a Tukey HSD test, this test essentially carries out pairwise comparisons of each group. Of course, this reveals a lot of data, because it tests not just the main effects, but every combination of the interaction by comparing average systolic blood pressure across all comparisons between treatment and gender groups. We would likely see a p-value below our alpha for each comparison of the treatment group, and for the comparison between male and female. But we will not see any p-values less than the alpha that compare across treatment and gender groups. Hopefully, this visual method can be beneficial for understanding the data and the most appropriate statistical test to adopt.